Thanks for the introduction. So right, this work is a short work that I've done with my supervisor Francesca Calore, and well, we uploaded it a few months ago. And as you see, this is about axion-like-particles and astrophysics in the sub-PeV range. Well, you could ask yourself, what is that and why should I care? So here's the reason why at least it's interesting to look at that. If we do indirect detection, you usually look for an exotic signal that is buried in a sea of strong astrophysics. And what do? Well, you have to get through the background to your signal. So for the sub-PeV range, which we here define a bit arbitrarily, from 10 TeV to 1 PeV, you have the special property that some of the astrophysical emission is erased. It is erased because of the extragalactic background light shown here, which is the second most bright component compared to the CMB that is, well, penetrating the universe, created by galaxies, stars, and radiation that is absorbed by dust and then re-radiated. And you see that, well, that's a quite extensive contribution. And if you now look at the path that gamma ray might travel with a certain energy, you see that at 1 PeV, you are limited to gamma rays that can at most come from the galactic center. If you go to smaller energies, well, those gamma rays might come from the closest galaxies, or you could go to the closest blazars at about 10 TeV. So the emission that you expect from extragalactic sources is reduced at these energies, which makes it a bit easier to search for exotic signals. So we would say that at sub-PeV energies, galactic physics should dominate the region of interest that we are going to analyze. And well, here we might now detect a contribution that is generated outside of our own galaxy. Okay, well, we can do that. Then how do we measure those sub-PeV gamma rays? So there hasn't been an astrophysics talk in this morning, so I'll go through it. So you detect these sources by ground-based telescopes, simply because those events are quite rare. The higher the energy, the less frequent those events would be, so you need a large area to cover to have good statistics in the end. How do you measure these particles that hit the atmosphere? Well, if those primary gamma rays hit the atmosphere, they create a particle shower due to the collision with molecules, atoms in the atmosphere. They can be quite extensive. They will travel towards the ground, and here you place your array of whatever you like. In this case, for those energies, you use water tanks to measure the Cherenkov light emitted by muons, for example, or you put scintillator arrays there to measure the charged particles that are created in this shower, and by this you reconstruct the origin and the energy of the incident primary gamma ray. Here are 3 examples. This one is HAWC, one of the experiments we will use. Here is Tibet, which is a smaller array, and this is LASO, the current generation most sensitive instrument in the sub-PeV energy range, with a, well, quite extensive area covered, about, well, 600 in radius, meters in radius. Okay, fine, we have that. Now, what did they measure in the end? I show here 2 plots. On the left-hand side, you see the measurement by HAWC, and on the right, the measurement by Tibet ASγ and LASO. This is from the ICRC proceedings, published by LASO. In red are the LASO points, and the little gray dots are the Tibet measurements. There are 3 points. And how are those data sets prepared? For LASO, they looked at a particular region in the sky from 25 degree in longitude to 100 degree in longitude, the same region that also Tibet ASγ has analyzed. But for LASO, they masked the known TeV bright sources and only kept the rest to get those data points, while for Tibet, they simply subtracted the events measured in the direction of the known sources. And this is exactly the same procedure that also HAWC applied to derive their measurement that you see here as a residual diffuse emission along the galactic plane. Well, the problem is that there is not sufficient information that is publicly available to manipulate the LASO data, so we do not consider LASO in our analysis, but rather stick to Tibet ASγ. Okay, so now to the actual signal that we want to study. So we borrow from an idea that has been born like 5-6 years ago, and this is linked to neutrinos. Neutrinos are, for example, generated in star-forming galaxies. Here's an example of that. In star-forming galaxies like our Milky Way, you have very high-energy cosmic rays. They might collide with gas or dust and radiation fields in that galaxy and create particles. For example, if a proton hits a photon in a radiation field or the CMB in that galaxy, you can produce a neutrino that travels towards the Earth, completely unhindered. It's a neutrino, very small interaction cross-section, and then IceCube might measure that. So by this you create an astrophysical flux of extragalactic neutrinos. Of course, you have also other processes like protons hitting other protons in the galaxy. Also that produces neutrinos, and in fact also gamma rays. Okay, so let's do that. If the proton hits another photon, it might also create this gamma ray. Now the problem is, of course, at those very high energies in the sub-PeV range, you have, as I said, the extragalactic background light and the CMB. Then those gamma rays get absorbed and you'll never see them on the ground. Well, the same is not true for the interactions that I mentioned when protons hit another proton, like gas. In a star-forming galaxy, here the energies are not as high as the sub-PeV range, and so you create an extragalactic background due to gamma rays. And this has been measured, for example, with Fermilab. You see here, this seems to be a cutoff at about 1 TeV, while this is the neutrino flux from astrophysical neutrinos measured by IceCube. Now, you do not want to spoil the Fermilab measurement, whatever we do in the following. So, now, if you again stick to this photon-hadron interaction, where a proton hits a photon, you can have in the star-forming galaxy a magnetic field that converts the gamma ray into an axion-like-particle. The axion-like-particle travels unhindered through the extragalactic background light. It might reach the Milky Way, and in the magnetic field of the Milky Way, it is reconverted into a gamma ray, and then you can measure it on the ground. And so you still get a gamma ray flux from those star-forming galaxies from a proton-photon interaction. As I said, you don't want to spoil the Fermilab measurement, so there has to be a cutoff at lower energies, and this has to be imposed by hand. So, this is exactly what we do, a bit more in numbers. You can link the spectrum of neutrinos to the spectrum of gamma rays with this nice equation, since they come from the same interaction. And, as I said, you have to impose a break in the spectrum of neutrinos that you then relate and get the gamma ray spectrum in a star-forming galaxy. To fix the flux, we use the best fit neutrino measurement of IceCube, which is a power law with this spectral index. And then we are left basically at this plot where you have the neutrino spectrum in source and the gamma ray spectrum in source at slightly higher energies, or the peak is shifted to slightly higher energies. And, well, what we elect now is the normalization here that we need in order to fix the strength of the flux that we expect, both for gamma rays and axion-like particles in the end. This simply comes from performing this integral, which is integrating the neutrino flux for all star-forming galaxies that might have existed in the history of the universe, given or relating this with a linear relation to the star formation rate density that we take from measurements, or physical measurements of that quantity. And so by matching the number that you get from this integral with the actual measurement by IceCube, you then have the in situ spectrum for neutrinos and gamma rays. Okay, now you have the gamma rays in star-forming galaxies, but you want axion-like particles, so we have to convert them. So the conversion is the usual story. You have a minimally coupled axion-like particle to the standard electromagnetic field strength tensor, so that you have either a decay of the axion-like particle, or you can convert it in an external magnetic field into a gamma ray via the pre-Markov process. So, how do you compute this? Well, we resort rather to a standard way, or a quite effective way to do it. with the so-called propagation equation that is written here in terms of a field that is decomposed into photons and an axion-like particle, and you might convert them according to those matrix elements here in the lower right corner of that matrix. What is usually done in this analysis is to say that any contribution from Faraday rotation is set to 0 because it's negligible, and then you see that only the component of an initial photon field parallel to the transversal component of the external magnetic field in a star-forming galaxy can convert into axion-like particles. Okay, this also is for the moment neglecting any absorption in the galaxy. So, how do you do this? Well, those quantities are all known. You can write down formulas, and this needs you to collect a lot of information about the environment in those star-forming galaxies, like the electron density, the density of the magnetic field that meets its orientation, and the field strength that you expect for these objects, as well as radiation fields that might be present in those galaxies. And then, in the end, to compute the number that we expect for the conversion probability, we resort to the typical thing that you do, a domain-by-domain analysis, saying that the magnetic field in a star-forming galaxy has a certain typical coherence length in which the orientation is fixed, and it also has a fixed strength. And then you go through domain, and at each step, you calculate what is the conversion probability, and then you simply multiply matrices. And in the end, you get the number of the probability that a gamma ray converts into an axion-like particle. As I said, this requires a lot of literature search to get all the numbers and all the ingredients you need. The final calculation is done with a nice code developed by Manuel Meyer and collaborators, gamma AWC. And, well, I just give you all the references to see what we do in terms of the properties. I just want to highlight here that for the properties that we are looking at, for example, the magnetic field strength, there should be some evolution with redshift. And in our approach, we assume that the magnetic field strength in those star-forming galaxies also increases with increasing redshift. Well, according to the description given here. Another thing that I want to say is that since we don't know what the exact properties of those quantities at a particular redshift are, we simply take a large number of realizations of possible galaxies and average over them to get the average conversion probability at a given redshift. Okay, that's the setup for the extragalactic part. Then you have to go to the Milky Way. Here it's a bit easier since we can, in principle, measure the magnetic field of the Milky Way. This is one model, the Jensen-Farrar model, that you use for that purpose. And in a very simplistic scenario, so a homogeneous magnetic field, the conversion probability is simply given by that formula. But of course, if you do the correct procedure, it's a bit more complicated, but it's also implemented in gamma AWC, so you can look it up for reference if you want. The thing is that in the end, you get the extragalactic axion-like particle flux, and to get the final gamma ray flux that you expect, you simply multiply that by the conversion probability in our own Milky Way. The extragalactic axion-like particle flux, if we go back to the initial formula for the neutrinos, is exactly the same, except for that you exchange here this source term to the first source term for axion-like particles. Okay, that's that. Now, what about the actual galaxy that also produces sub-PeV gamma rays? As I said, this is mostly dominated by galactic physics, so there are two main contributors here. Interstellar emission, which is the emission coming from cosmic rays hitting gas radiation fields in our own Milky Way, and this produces very high energy gamma rays in quite a diffuse manner, and subthreshold point-like and extended sources, because the bright ones have already been subtracted from the data set, so that only the subthreshold sources would survive the subtraction. For the interstellar emission, we use a recent model shown here, for example, above 100 TeV along the galactic plane, so it's quite diffuse. And here you see the region of interest, for example, for LASO, the same for Tibet, where we put our analysis exactly in. And this data set, or this model, better to say, has been fit to be consistent with Fermilab data with Argo data, with LASO data, and also with Tibet ASγ data. And the good thing is it comes in two versions, a maximal and a minimal scenario of emission, so that we can also gauge the uncertainty that we would expect because of the insufficient knowledge of the modeling of this component. So this is all fine. Then to the subthreshold population. Here we have to do a bit more of a modeling, since this is quite unknown in the TV range. And also if we then extend it to the sub-PeV range, of course. So for this we adopt a model that has been developed in this paper, and we slightly modify the parameters to fit our needs and to update a bit. In principle, it's quite simple. You have a source population that you can separate into a spatial part, where it's simply distribution of sources in a galaxy, and an intrinsic luminosity function of the sources, how bright they may be, at maximum, at minimum, and just draw from that. This kind of distribution has already been fit by that group to the HAWC galactic plane survey results, so that is more or less fixed. And distribution of sources, if you're interested, is coming from the best fit pulsar distribution in our galaxy. The main assumption of this model is that all the sources that the subthreshold population consists of are pulsar wind nebulae, which is a particular kind of objects, and they all share the same common gamma ray spectrum, shown here. It's an exponentially cut-off power law. And if we, for example, go to the TEFCAT catalog, which lists all known TV bright sources, we can determine the best fit spectral, the average spectral index of those sources with such a spectrum, which turns out to be 2.6. And as I said, we need to impose a cutoff, and we choose for this cutoff 300 TeV, since this will be very well in line with the statement by Tibet that above 400 TeV, they did not measure any gamma ray in the direction of a known TV bright source. Then in the end, you perform this integral, where you first integrate out the spatial dependence of your model, and then you do a shift of variables to fluxes instead of luminosity, and you derive out of this formula. And the last part you need to know is the detection threshold of your instrument. Well, and that is some kind of business. So let's go into that. What did we do here for Tibet ASγ? There is a statement in the paper that 37 sub-PeV gamma rays have been detected in the direction of all known TV bright sources. Okay, you can interpret this in a quite optimistic way, saying that the 37 most bright sources should have contributed at least one photon to that. If that's the case, well, we don't know, potentially not. So of course, the brightest source will contribute, I don't know, a lot of those photons, but at least that's the most conservative thing you can do to get a threshold. It might be higher in the end, but okay. That's just in our favor, if it's higher in the end. Okay, now we collect the spectral information from, again, TEFCAT, as I mentioned earlier. And if you do that, you can use the exponential cutoff power law. If there is no cutoff in the spectrum themselves, you can impose that too. And then simply calculate the flux that you expect and compare it, for example, to the flux of the Crab Nebula in the same energy range. And this shows the cumulative histogram of those sources. Then in this histogram, you go to place number 37. You look at the flux level, and that should be your detection threshold. In this case, it's about 10% of the Crab flux at best. It might be higher. For HAWC, this is easier, since they report the sources that they used to derive the measurement in the end. So you simply take the source with the lowest flux, and that is approximately the detection threshold. And in this case, this is 2% of the Crab flux in the relevant energy range. Okay, then you have collected all of that, and that's your model that hopefully fits the data. Okay, how do we fit the data? The data is fit in a very simple manner. It's simply a chi-square fit in the end, given by that. Just to say that the HAWC collaboration provides the measurement in terms of a power law, so it's not bins. For this kind of analysis, we want bins, so we first bin the data. Okay, well, that's trivial in the end. Another thing that I want to mention is that as soon as you turn on the coupling of axions to gamma rays, also the galactic contribution is part of that conversion. So you cannot simply take those models at the naive value that there is in the model files. Since also particles produced at the galactic center might convert to axion-like particles, and as those never reach the detector as a gamma ray. So this is taken into account, and we just indicate this here by this parameter theta, just to make it clear. Okay, now let's first check what happens with the astrophysics. So if you concentrate on the green and purple lines, you see only the astrophysical emission. Here, the subthreshold contribution in green, and in light purple, the interstellar emission contribution for both experiments. And in dark purple, that's the sum of those two contributions without any axion-like particle existence. And we split it here in the minimal and maximal scenario for interstellar emission to make it clear, and both of those models seem at least to fit the data as it's, well, this is considered energy range, so it's not a bad fit to the data at all, and given the uncertainty of the measurement. That's fine. That means that the final limits on axion-like particles are quite strong in the end, and you can expect at least to gain something from this exercise. So we did it here. For example, if you look at an axion-like particle of 100 nanoelectron volts, then you get an upper limit using the maximal scenario of interstellar emission of this number, and in fact that's competitive given other limits you derive, current state-of-the-art limits in the TeV, sub-PeV range that are on the market. To do this more quantitatively and to show you the evolution with axion-like particle mass, this is the plot that we derived in this case. So the upper panel shows you the uncertainty due to the interstellar emission with this minimal and maximal emission scenario, and the variation you induce here is about a factor of 1.5. If we do not include any astrophysical modeling, so simply go and say, well, our axion-like particle signal is not supposed to overshoot the data, then those constraints are worsened by a factor of about 3. But even in the minimal scenario for the interstellar emission, you are competitive with current bounds on those particles from TeV energy range experiments and measurements. The other uncertainty here is, of course, the modeling of the magnetic field in star-forming galaxies. Well, what do we know about that? Well, there are papers that have tried to determine the magnetic field in nearby galaxies. We use that. But the evolution and formation of galactic magnetic fields is a topic of ongoing research, and it's far from being settled. So, of course, we say that the magnetic field strength increases with increasing redshift, but that is not guaranteed. So, well, what we did is, hey, what happens if we just fix the level of magnetic fields that we have in nearby galaxies for all redshifts and go with that? And if we do it, we arrive here at this line, which is again about a factor of 1.5 deterioration compared to the case of redshift-dependent magnetic field dependence in the maximal emission scenario for interstellar emission, to say it again. And this means in the end that we are not too sensitive to the very high redshift sky. Our, well, sensitivity ends about a redshift of 2, in fact, if we look into the numbers. Then in the beginning I said we would exclude LASO, but just for the sake of the exercise, let's try to do it anyway. Okay, so there is scarce information about how this thing has been derived. Well, there's this mask, there are numbers. What we did is digitize this mask as best as we can. It's a low resolution, so well, you can try. And then you apply the same source mask to your analysis. We have no idea what the detection threshold of LASO is. There are no numbers. So, well, we forget about that. Only put in our interstellar emission model. And, well, we hope for the best. And here on the right, you see the results that you get for those two interstellar emission models that we have and LASO data, as they are here shown in the ICRC proceeding. Okay, you see, well, it's not as good as combining HAWC and Tibet, as we did in our initial analysis. And please don't quote me on this, because there's another group that did the same exercise, so they have the right to publish their results. That's just to illustrate what you could gain with LASO. So, in the future, if LASO is so nice to provide us with information what they actually did in their experiment, would be good, then this is quite promising, since LASO is quite sensitive to a large range in energy, spanning both the HAWC and Tibet energy range. So LASO is a great telescope. We hope for the best. Okay, this brings me to the conclusion of our exercise. So, as I said here, what we try to do is to search for an exotic signal that comes from star-forming galaxies, produced by photo-hadron interactions that produce neutrinos, but also gamma rays, and those gamma rays might convert into axion-like particles because of the presence of magnetic fields in star-forming galaxies. Then, they are not absorbed by the extragalactic background light, so they might reach the Earth, and that gives us a handle on modeling both the galactic astrophysics as well as the extragalactic component that we expect from axion-like particles. And if we look for them in the dataset of HAWC and Tibet ASγ, we find that the models currently on the market that describe the astrophysics fit the data, and that an exotic contribution is, well, rather constrained, so that we derive competitive results given in the output parameter space, which I've shown you. And, well, in fact, the number here seems to be our final result, and in this case, we progressively close the gap to currently existing experiments that also test the same mass range as those sub-PeV gamma rays have the ability to. I thank you for the attention. I stop here.
Thank you so much. Are there any questions from the audience? Yes, I see one right here. Someone with a microphone nearby, or shall I come up to you? Who else is here?
Thank you, Kristen, for the nice talk. I have one question. Do you include photon dispersion on the interstellar radiation field and absorption? Because we are talking about like 100 TeV to PeV gamma rays that can be absorbed in the interstellar radiation field.
Right. Yes, we do. So we include that. So the initial formula that I've shown you a few slides back in this matrix formalism did not list that there is absorption, but of course that is present, and we do model that and include this also in the results. So this is taken care of. Of course, this depletes a bit the tail at energies above 100 TeV, and so you are, well, the most constraining power comes in fact from the range from 50 TeV to 100 TeV in this case.
Thank you. Any more questions? Yes,
No question, but a remark. I think it is a good thing that your limit does not contradict to our experimental results generally.
Okay.
That's a question right there.
Thanks for the great talk. So a few slides back, you said there's this domain length for the magnetic field is about a kiloparsec. So you said.
Right.
I'm curious if you can maybe say a few words where that comes from and how sensitive the results are to the value of that particular parameter.
Right, so this falls in the category of astrophysical papers that try to determine extragalactic magnetic fields. So that number comes directly from a recent survey of 28 nearby star-forming galaxies. And the researchers in that paper tried to determine what is the coherence length of the magnetic fields that you find in those objects. And the general result was that it is about 1 kiloparsec. You do this by observing the usual the rotation measure induced by I think radio measurements in those galaxies. I'm sorry, I'm a theorist, so if I say nonsense, well, that's nonsense. But at least that's what I got from the paper. They tried their best to reconstruct what they get in terms of their measurements. We just believe them.
How sensitive?
So at least there are 2 surveys that we found in literature. One is a bit older, one is a bit more recent, and they come to the same conclusion in the end. So
how sensitive are your results?
Our results are sensitive in the sense that if you increase the coherence length, that's not a problem. If you decrease it, well, that is kind of, well, it's not problematic, but you are sensitive to that. So you might deteriorate the limits about a factor of 2 if it's really small. but those very small coherence lengths are expected for starburst galaxies. And starburst activity is limited to a very small central part of the galaxy of about at most 500 parsec, and only at higher redshifts. So for star-forming galaxies, that seems to be a larger coherence length, at least for the regular component of the magnetic field.
Thank you.
We have a question here right in front of
Yeah, thank you very much for the very nice talk. Can you do anything meaningful with some sources? Just looking at spectra which has been measured, neutrinos have been seen, maybe we get some limits, and also can you derive limits on axions?
That's a good point. So in fact, especially for those sub-PeV measurements, also we would expect that those experiments like LASO, HAWC, and Tibet ASγ provide measurements in the direction of known bright extragalactic sources. Then you could really try to stack even those events and see if there is some kind of deficiency of gamma rays or things like that. So I think it hasn't been done. It might be done in the future, but you also need good models for the magnetic field in those objects. And, well, I think there are experts here that do that.
On the front row question, but meanwhile, also, I see someone in the back.
Okay, thank you, Mr. Lee, for the last talk. So I will have one question about the realization of the E field. So, I think in the slides before you said so each domain have a different direction of the E field. So do you run a simulation for this E field, or because in the end you said again like you use a constant E field model, like you so I was a bit confused by that.
Right. Yeah. So by constant, I mean the strength is constant, but the orientation is still varied from domain to domain. So yeah, this is kind of like a random walk. So it's just randomly drawn from 360 degree, basically, the orientation.
Okay, for the galactic magnetic fields, you use the axion-like-particle model, right?
Yes, exactly.
Okay, nice.
All right, Ima.
I just have a follow-up question. So you say this 1 kiloparsec coherence length between the galaxies?
No, inside the galaxy.
Inside?
Inside,
Okay. Then it's some plasma.
Yeah.
Plasma,
Yeah.
I'm just wondering, in the equation when you derive your gamma ray flux, you assume a star emission rate density evolution, and you said for the entire history of the universe, but in practice, what redshift do you actually go up to?
Well, in practice, the results vary throughout the literature. You find results that extend up to 4.5. You might also find results that extend up to 10. They seem to be in agreement in a certain uncertainty band. So, well, that's one particular example we picked. But in this reference, you also find some, well, variation of the prescription. We just check what happens if you take a very aggressive or a minimal realization of that, and well, the impact that you finally have is like negligible. So that's not a problem.
Any more questions? I do not. Yeah,
One question now.
Okay.
Is it possible that if you look near to the sun, that you get, because we have much more photons around the sun, that you get some shadow or whatever from the sun which is so much bigger than the sun itself?
Okay. Now you've caught me here on the spot. I don't want to say nonsense, so I don't say anything. I don't have the answer. I don't know.
Okay. No problem.
Okay.
Last chance. Any more questions? If not, let's thank the speaker once more.